Welcome to the solutions to problem set number 8. We start by proving proposition 9, namely that Sn, together with composition of maps, is a non-abelian group if n is greater or equal to 3, and that its order is n factorial. So first of all, we have to convince ourselves that composition of maps is an operation on Sn, meaning that if I take two permutations and compose them, that this again is an element of Sn, meaning a permutation of the numbers 1 to n. Now, if you're familiar with bijective maps, this is obvious because the composition of bijective maps is again bijective. But for those who are not so familiar, let's look at an example. In the case n equals 3. Bijective means that here and here I have exactly the same numbers up to the order of the numbers. So this is a bijective map from the set 1, 2, 3 to itself, and this here as well. This would not be, because two different elements would get mapped to the 3 and the 2 would be missing in the image. So this is not bijective. But then the composition of this map here with this must again be bijective, because both maps give me a one-to-one correspondence of the set 1, 2, 3 with itself. So it's not surprising that the composition is again bijective. So let's do the composition together. 1 goes to 1, 1 goes to 3, so 1 goes to 3, 2 goes to 3, 3 goes to 1, 3 goes to 2, 2 goes to 2, and as we can see, this again is a bijective map. This of course is no proof, but just to illustrate the concept of a bijective map again. And in general, one can show bijective means exactly that there is an inverse map, and the inverse of this is simply that. All right. So this shows that this is indeed an operation on Sn. And now we have to check the group axioms. Is this composition here associative? Yes, it is. Composition of maps always is, as we already proved on problem set number 1. I need a neutral element or an identity. This, of course, is the identical permutation that does nothing to these elements, just leaves them as they are. This clearly is the identity because it composed with any permutation is the same as this permutation and the same the other way around. This should be clear. Is there an inverse permutation? By definition, because a bijective map means exactly that it has an inverse map. And it is easy to write down, simply read from bottom to top. So the inverse of this map would be 3 goes to 1, 1 goes to 2, 2 goes to 3. And there's no need to formalize this to n elements. This simply should be clear. So this shows that we have a group. Sn together with composition of maps is a group. Now for the order of this group, let's find out how many permutations of these numbers are there. So here for the first entry, I have n possible choices. Could be any number from 1 to n. Now, because the map must be bijective, for the second entry, this here is already taken. I only have n minus 1 possible choices left. Then for the third entry, n minus 2, and so on. And for the last entry, there is only one possible choice left, the only number that I haven't chosen here before. So this gives me n times n minus 1 times n minus 2 and so on. So exactly n factorial possible different permutations of this set. So the order of this group here is n factorial. Right now I simply explain the ideas. This is not written down perfectly, of course, so you should hand this in when this is on your exercise sheet at the university, for example. So now, is this group abelian? No, it is not. Clearly S2 consists only of these two elements. Those are the only possible permutations of a set of two numbers, and every group of order 2 is commutative. This is trivial. We wrote down the group table. Back then there's no other possibility. So let's take a look at S3 or Sn for n greater 3. And now we use the cycle notation. So we take these two transpositions and compose them. So 1 is not affected here. 1 goes to 2. 2 goes to 3. 3 is not affected by this one. So we have 1, 2, 3. Let's check 3. 3 goes to 2. 2 goes to 1. So 3 goes to 1. So this composition is this 3 cycle here. Now let's change the order. 1 goes to 2, 2 goes to 3. Aha! So 1 goes to 3. 3 goes to 2, and 2 again goes to 1. And those are not the same 3 cycles. They have different effects on the number 1, hence they can't be the same. This shows that S3 is not commutative, and actually Sn for n greater or equal to 3, because these transpositions lie in every Sn. They lie in S4 and S5 and so on. So this is enough to show that Sn is a non-abelian group if n is not 2. And of course n equals 1. S1 is simply the identity or the one cycle 1. This clearly is a commutative group. I forgot that, but no one talks about S1. All right, that's already it. Written down very sloppily, but I hope you could understand the ideas. So I won't put an end of proof box here because this was clearly not written down very well. Okay, exercise number 2. We find the cycle decomposition of this permutation in S6. So we start with 1, open this parenthesis, 1 goes to 3. So I have the 3 here. Next, 3 goes to 6, so I have the 6 here. 6 goes to 4, and 4 again goes to 1, so I have a 4 cycle and the parenthesis closes. The next number that is missing after 1 is 2. 2 stays where it is, and the same with 5. 5 stays where it is. So this is simply a 4 cycle. Those 1 cycles are cancelled or left away. So I have 1, 3, 6, 4 as the cycle decomposition. Okay, the same for pi, this permutation. 1 goes to 4, 4 goes to 1, so I start with a transposition. Next, 2, 2 goes to 6, and 6 goes to 2, so another transposition. And then 3 goes to 5, and 5 goes to 3. So this here is a product of 3 transposition, 3 disjoint transpositions. Okay, number 3, also trivial, but nothing's trivial until you see it. Let's take an example. I take 1, 2 and 5, 6. And then I take 5, 6 and 1, 2. I most of the times omit this circle here for composition because it's clear that we are composing maps. So we need to show that these here are the same. This exactly means that those disjoint transpositions commute, or actually disjoint cycles. It's always the same argument. Oh yeah, and then the problem, there are cycles. So whatever, take a 3 here, 5, 6, 3. So what does it mean for two maps to be the same? It means that if I apply them to all the numbers from 1 to n, I must get the same result. Then those maps are the same, because they are maps from the numbers 1 to n into themselves. So if I is none of those numbers, for example 4, then both of them leave the 4 where it is, so both of them give me 4. So this is the same. Now if I take a 3, for example, then here the 3 gets mapped to 5, but because they are disjoint, this 5 has nothing to do with this transposition, so the 5 stays where it is, so 3 gets mapped to 5. The same here, this guy leaves 5 where it is, and here 5 gets mapped to 3. You get the idea. 3 stays where it is, and here 3 gets mapped to 5. So both agree on the number 3, and so on. And this clearly shows that disjoint cycles always commute, because the order here doesn't matter at all, because all the numbers here have nothing to do with the numbers here. They are left invariant. And that's it. But it's good to remember, whenever you have disjoint cycles, you can permute the order as you wish. All right, we need to find the inverse of this 4 cycle. As I've explained in the video for lesson 8, you simply write the numbers in the backwards direction. So 6, 5, 3, 2. But then we agreed to start with the smallest number. So here I have 2. And now I have to read cyclically 6, 5, 3. So I push the 2 here and the others I push back. And now those composed should give me the identity. Let's check this. Pi composed with pi inverse. If I plug in the 1, nothing happens at all because the 1 does not appear here. So 1 stays where it is. If I plug in the 2, 2 goes to 6, 6 goes to 2, so 2 stays where it is, and so on. And if I plug in the 6, 6 goes to 5, 5 goes to 6. So indeed, this is the identity, and also the other way around. So this is indeed the inverse of this 4 cycle here. Then we're supposed to write this as a product of transpositions. Of course, not disjoint transpositions. This is not possible. All right, so this should do the trick. 2, 3, 3, 5, 5, 6. Let's check if this is true. If we plug in 1, nothing happens. If we plug in 2, nothing happens, 2 goes to 3. Checks out. If we plug in 4, nothing happens on both sides. If we plug in, oh no, I forgot the 3, sorry. If I plug in 3, 3 goes to 5. Nothing happens, 3 goes to 5. If I plug in 4, nothing happens. If I plug in 5, 5 goes to 3. No, sorry. If I plug in 5, 5 goes to 6. Nothing happens with the 6, and indeed 5 goes to 6. If I plug in 6, 6 goes to 5, 5 goes to 3, 3 goes to 2, and indeed 6 goes to 2. So this is one possible way to write this as a product of, in this case, 3 transpositions, but of course they are not disjoint. Otherwise I would have 2 different ways to write a permutation as disjoint cycles, and this is not possible. This is not the only possibility. There are several ways to do this, but since we're only asked to do it one way, I will leave it at that. Okay, exercise number 5 is a little bit more interesting. I never got used to this. In America, they always use this for number of. That's not a thing in Germany. So the number of 4 cycles in S7. So let's think about that. Okay, so how many choices do I have to build a 4 cycle? For the first number, of course, I can take 7. I have 7 choices. Then here only 6, then only 5, then only 4. No number can repeat itself. But this is not the answer yet. So it would have 7 factorial divided by 3 factorial or 7 minus 4, so that we can generalize it to m cycles in Sn. But this is not the correct answer because, for example, 3, 4, 6, 7. If this is a 4 cycle, then changing these cyclically, meaning 7, put 7 in front, and then 3, 4, 6 is exactly the same cycle. So we can't count these as two different cycles. And then again, what is the number of cyclic permutations? In this case, 4. I have 4 possible numbers that can be in front, and then the rest is defined by this order here. So I have to divide by 4. So this here divided by 4 is the correct answer. So then this is easy to generalize because I take n factorial divided by n minus m factorial. This is the 3 here. Oh, and for this is just short for this here, because 7 factorial would be down till 1, so I have to divide by this here if I want to use the factorial notation. So this is just a short way to write this product here. If you do not like that, you can write it as n times n minus 1 times n minus m plus 1. This would be the product notation. But then we have to divide this here by m because of the cyclic rotations of the numbers. So this would be the answer. Those are this is the number of m cycles in Sn. And obviously m needs to be less than or equal to n, otherwise it's not possible. Now let's look at the special case, m equals n. How many n cycles are there in Sn? If this formula is correct, we have n factorial divided by n times 0 factorial. This is defined to be 1, so we get n factorial divided by n, which is simply n minus 1 factorial. Yeah, this is at the first look a bit surprising, but look at S7. I would have 7 factorial possibilities, but 7 cyclic permutations fall away because they are the same cycle, so 7 factorial divided by 7 is 6 factorial. So this is the number of n cycles of length n in Sn. Okay, part B. We are supposed to find the number of permutations in S7 that are a product of 2 disjoint transpositions. So how do we do that? Here I have 7 possible choices for this first number, then only 6 remain. They need to be disjoint, so I'm left with 5 and 4 because I can't repeat any of these numbers. So I would get, but here obviously I can change the order, so 4 possibilities go away. And because disjoint transpositions commute, as we thought about in exercise number 3, if I switch the order, this also doesn't give me a new permutation, so I have to divide by 2 times 4. The 4, because 2 times 2 here, switching around the numbers doesn't give me a new transposition. And here, this is 2 times 2, and switching those transposition. So gives me the number 8. And this is easy to generalize because this argument never changes in Sn. I always have the factor 1 over 8 because of the switching that I just explained. And here I have n times n minus 1 times n minus 2 times n minus 4, which again I could write using factorials, but it's not really necessary. Okay, so this was a little combinatorics applied to the number of permutations, certain permutations in Sn.